Morning, everybody. I want to start out today with showing you a short reaction. Let me see, can you all see my video screen? I wanted to show you this candle, and you know when you light it, you get a chemical reaction between the wax and the air. You have oxygen reacting with the wax to create the flame, and if you put a beaker over it, you can see that the flame gets dimmer and then it goes out. And if you take the beaker off, I don't know if you can see this or not, but there's condensation in here. And so that indicates that you had one product form, which was water. And usually it's gaseous, but it can cool back down to liquid form. The other product was carbon dioxide, which you can't see, but it's in the smoke. So the flame went out because you limited how much oxygen was present. So the reaction, let me write on the whiteboard so you can see that. And get this set up really fast. It's a combustion reaction where you're combusting the wax that's being burned along with the wick. So if you were to see it in chemical form, you'd see this. So the wax reacting with oxygen, let's write that as O2, goes to form carbon dioxide and water vapor, which we saw as water after it cooled back down. So when I put the beaker over the flame, I limit the O2. So when I put it in a closed area, the amount of oxygen present is limited. It's only in the beaker. And then once that runs out, then the flame is going to go out because there's no more oxygen present in the beaker. We've limited this reactant right here. And once that reactant runs out, the reaction can't continue. The reaction in this case is the flame. So when you're looking at any kind of flame or fire, what you're seeing is a chemical reaction take place. It's a combustion reaction between oxygen and whatever is being burned. But if you remove the oxygen, then the fire goes out because you need both reactants for there to be a fire. Okay, if you're looking at this reaction, H2 plus O2 forms water. We'll have to balance it first. So we put a 2 in front of here. Now we have 4 H's, put 2 over here, 4 H's on both sides, 2 O's on both sides, so it's balanced. So I said yesterday that you can think of it this way, that the number in front of here can represent a number of molecules. So we could say, well, we have 2 H2s reacting with 1 O2 to create 2 H2O molecules. Or we could say that we have 2 moles of H2 reacting with 1 mole of O2 to create 2 moles of H2O. And that's a more useful way to think of it. We can also relate these as ratios. And what we can say is that for every 2 moles of H2, we need 1 mole of H2O. I'm sorry, we need 1 mole of O2. So for every 1 mole of H2, for every 2 moles of H2, we need 1 mole of O2. That's what's called a molar ratio. So this would apply if we were to double this. If we were to multiply everything by 2, what we would say is we need 4 moles of H2 for every 2 moles of O2. And so this ratio would apply for any number of moles we had. Whatever moles we have of O2, we need twice that of H2. So we can relate the reactants that way. And this is basically the recipe, we could say, that in this reaction, you have H2 reacting with O2. For it to work, we need twice as much H2 as we have O2. And the simplest ratio would be 2 to 1. But you could also write as 4 over 2. Now it's like a fraction though, you usually reduce it to 2/1 if you can, but it's the same ratio in both cases. It's double on top than on the bottom. Now we could flip this around too. We could also write it this way, where we'd have 1 mole of O2 over 2 moles of H2. So these ratios can apply in both ways. It just depends on what we need. Let me show you what I mean by that. Okay, so let's say that we have available for us 3 moles of H2O. Sorry, 3 moles of H2. Okay, so the recipe says that whatever we have of H2, we need half of that of O2. So if we have 3 moles of H2 available for us, then we would need half of that of O2. So we would need 1.5 moles of O2 to react with 3 moles of H2. Now, if we didn't know how to figure that out just by looking at this, we could use a ratio to determine that. So if we're asked in the problem, if we have 3 moles of H2, how much do we need of O2? And we weren't sure how to figure that out, we could use a ratio to do that. So we could take 3 moles of H2 and multiply it by the ratio, which we would need to cancel out the H2 and get O2. So we have 1 mole of O2 for every 2 moles of H2. H2's cancel out. We're left with O2. So we would do 3 times 1/2, which would give us 3/2 or 1.5 moles of O2. So that's how we use molar ratio. So it just depends on what we have, what we've been given, but they can go any way. So you could write it as 1 mole O2 over 2 moles of H2, or 2 moles of H2 over 1 mole of O2. It just depends on what you need to figure out. So these ratios are used to determine how much you need of a certain reactant or of a product. So we related these 2 reactants. We can also relate a reactant to a product as well. So if you wanted to know how many moles of H2O you'd get in this reaction, you would take either one of these reactants and relate it to the product. So we could relate H2 to H2O and say that for every 2 moles of H2, we would get 2 moles of H2O. And that would be our molar ratio between this reactant and that product. You could also relate O2 to H2O and say that for every 1 mole of O2, you get 2 moles of H2O. These could be flipped too if you needed to. Again, it depends upon what you've been given, what you need to figure out. But any one of these can be related to each other. It doesn't matter if on the same side or on different sides. You can use it to predict any amounts of reactants or products in a reaction. So homework today, all they're going to ask you to do is write out molar ratios. You're going to just write out the reactants over the products. And in a reaction, you'll just write out each of them. Let me give you one more example before we go on. So yesterday we looked at this reaction with propane and oxygen. So C3H8 plus O2 gives us CO2 and H2O. We would balance that. I have my book really fast. So we would have 5 O2s right here, 3 CO2s, and 4 H2Os. So today I'll ask you to just get molar ratios. And we would relate everything in this reaction. So we could relate propane to O2. So we would say for every 1 mole of C3H8, we need 5 moles of O2. And anytime we have one of these, we can always flip it around. So we can also write it like this, where it's 5 moles of O2 over 1 mole of C3H8. We could relate this reactant right here to this product. So we could relate propane to carbon dioxide. For every 1 mole of C3H8, we would have 3 moles of carbon dioxide. And that could also be flipped around too. We could also write as 3 moles of CO2 over 1 mole of C3H8. We could also relate either of these products to the other, either of these reactants to their products. So we could also relate O2 to H2O or C3H8 to H2O. So we could also say that for every 5 moles of O2, we would get 4 moles of H2O. And we can say that for every 1 mole of propane, we would get 3 moles of CO2. And these could also be flipped around. I don't have room for that, but you could flip these around too and write as 4 moles of H2O over 5 moles of O2 and 3 moles of CO2 over 1 mole of C3H8. So there's a lot of combinations in these. And again, it just depends upon what you're asked to find. For today, for homework, they won't ask you to find anything, just write out the ratio. So all you'll be doing today is writing out what I just showed you on here, just relating each reactant to each product or each reactant to each other. Like I showed you right here, I related C3H8 to O2 for these two. Then I related one of the reactants with one of the products by putting C3H8 over CO2. So you can relate reactant to product, reactant to reactant, reactant to the other product, product to product. So all of these can relate to each other. And that's the main idea to know today. Are there any questions about this before we go on? Okay, so for today, work on page 372. Do question 4 and then question 9. So just 4 and 9 today on page 372. And they'll be just doing what I just showed you today, writing out molar ratios. So it's page 372, questions 4 and 9.